Good afternoon, everyone. Thank you for those of you that have joined live. It's always nice to have some kind of audience, even though we can't necessarily be in person at all these events at the moment. Quick intro on me. My name's Steve. I'm a Microsoft MVP, Pluralsight author, and engineer for Elastic. I work there maintaining the .NET language client. So if you've used Elasticsearch.net or Nest, you are using the tools that I'm now maintaining and the libraries that I'm looking after. You can follow me on Twitter at Steve J. Gordon. So if at any point after the session you have any questions that suddenly pop into your mind, please do send those to me. My blog, stevejgordon.co.uk, has a lot of what I'm going to cover today in quite a lot more verbose form. So again, if stuff sort of resonates with you, but you miss some bits and you sort of want to go deeper, you may find some posts there that will help you along the way. And I will highlight there's a bit.ly link there on this intro slide, bit.ly/hyperf.net. That will take you to a link with all of the slides and the code that I'm going to show you today as well. So that will help you along if you want to kind of catch up after the event. With that, I'm going to go straight in because there's a lot that I want to cover. So the first thing I want to touch on at the very beginning is what is performance. Everyone may have slightly different interpretations of what this means for their applications, for their situation. So we'll just kind of level set on what I mean when I'm talking about it today. We'll talk a little bit about how we measure application and code performance. That's quite important if we're going to talk about performance. And then I'm going to start introducing some stuff. So the key goal here is this is quite advanced topics, but hopefully from a sort of beginner to those topics level. So it's kind of trying to take you on a journey that I've been on over the last couple of years of trying to understand how a lot of this stuff works, where it can be applied. And that's just come through prototyping and playing around with these features. So some of the features we'll touch on are things like span of T, memory of T. We'll talk a little bit about ArrayPool, system IO pipelines, and System.Text.Json. So tons to cover, and I will dive straight in. Aspects of performance then, what I'm talking about when I say performance for the rest of this session is kind of touched on by three key areas. So the first thing I'm thinking about is execution time. How long does a piece of code, a unit of code, even a line of code take to execute? What you need to measure depends on what you're doing and your own application requirements. But really, we're talking about how fast the code can actually execute, you know, when that method gets called. How long does it take before it returns to you, that kind of thing. At a higher level, we have throughput, and this is still a useful measure of performance, but a sort of a more realistic measurement that you can perhaps track in production, as well as just measuring it when you're testing. Throughput could be things like how many requests per second can your application handle, how many messages from a queue can you process in a given amount of time. It's kind of a more real-world measurement of what your application can achieve at a unit of scale that you want to deploy it at. And this is obviously going to be linked to execution time. Something that executes more quickly in the code is potentially going to have higher throughput, but that doesn't necessarily match up. There's all sorts of contentions that you may have. It's not just how much time is spent in the CPU, but it could be the amount of memory that's going on, how many objects you have causing memory pressures, I/O for network and files. So throughput can be affected by a lot of things, but it's a good measurement to have not only as you're developing, but also in metrics that you measure with your deployed production applications. And then finally, and probably of most interest to most people, we'll be thinking about memory allocations. .NET is very fast at allocating new objects. When you do new something, you get access to that and the reference back to that really quickly. And so we can be tricked into thinking that there's no real overhead. Unfortunately, there is some overhead later on. All of this memory that we're using in terms of new objects that we're allocating on the heap, at some point in the future, the garbage collector is going to need to run to reclaim some of that memory in most situations. And so one of the things we can do in our applications to reduce the cost of those GCs, which although they're very, very fast and may not pause your application for very long at all, can have an impact at high scale. One of the things we can do to avoid them is by avoiding allocating objects in the first place. And then that leaves us in a situation where there is nothing for the GC to collect. And we can also run the applications potentially on smaller memory footprints, smaller container images, that kind of thing. Of course, performance is contextual, and everything I'm going to show you today is kind of for the extreme end of the 1% cases where you might actually need to do it. So I'm always conscious of making sure that people don't leave this talk and immediately go and spanify their whole code base. because Steve showed them in a talk. The tools are there, and it's worth being aware of them and understanding when and how they can be applied. And then deciding when to do that is kind of down to you and your applications. Do you have something that has to scale in a huge way that could potentially be optimized? Have you got a process in your business that takes a long time and that costs you money, costs you customers in some form? Do you want to go and optimize it? So for your situation, you need to decide if applying high performance techniques is right for your app. And there's a real important trade-off when you get into performance. So the trade-off is between performance and readability. The more performant code, as we'll see when we get to the more realistic examples later on, the more performant code tends to be more verbose, more tricky to read, more tricky to maintain. And that's a cost that you need to balance up in your own business as well. If you've got an application that's being regularly worked on by lots and lots of developers, you probably want that code to be self-explanatory, easy to read, easy to maintain, easy to test. And so erring on the side of readability is a good practical decision for your business. On the other hand, you may have an application, maybe it's a microservice that's built, it does one thing, it's already doing it well, so you're unlikely to go in and tweak it all that often, but it has to scale a huge amount to be able to keep up with load. Well, perhaps that's a situation where you can trade off the readability and the ease of maintenance of that application for looking at optimizing it, making it more performant to get a cost benefit on the other side of the coin. So this is the trade-off you need to sort of play up in your minds. And this is why performance is really going to be contextual to your situation and your applications. So I want to touch on the optimization cycle that we're going to be covering today. And the first, most important point is before you do anything around optimization, measure your code. Measure it at the high level, so profiling your application that we'll touch on in a moment, allows us to understand, what are the hot paths in the application? Where is the memory pressure? Where is the memory allocated most? What methods are called most often? They're the areas that if you are going to optimize the code are probably where you should be focusing first. So measure, profile, understand the application performance as a whole, then go in and measure the code that you're planning to change. And by measure the code here, I'm talking about benchmarking. Take a benchmark of how the code performs today, make your change, optimize the code, and then measure again. And do this in very small increments. Don't optimize huge swathes of your application in one go. Go in, change maybe 1 or 2 lines, apply an ArrayPool, the span of teeth feature where it's applicable, and then measure again to validate your assumption is correct. Does that actually, in this situation, in this code path, make the difference you hope it does? If it does, great, continue. Otherwise, maybe roll it back and try something else. Ultimately, this is a cycle that you will keep doing until you either reach what you think is the absolute performance that this piece of code can do. Maybe you get down to 0 allocations and you're pretty happy. Or you might get down to a point where you think, well, actually, we've halved the execution time. That's what we were aiming to do. Let's move on. So be practical about how much of this you apply and for how long you keep applying it. It can be a bit of a kind of continuous dream to chase the 0 allocations. And in some situations, that can be a bit of a fool's errand. So think about how you're applying this. In terms of measuring app performance, there's a few tools that I recommend. So if you're a Visual Studio user, the diagnostic tools is a good starting point. These tend to boot up these days when you start debugging automatically, and they give you a bit of a profile of the memory as the application's running. Now, remember, you aren't on release build code, so there are optimizations that may be missing from your code for the debugging session to function, but it's still a good view and an idea. You can see if huge allocations occur as you're testing the app, as you're debugging through it, and maybe then focus in on those more closely. To do full profiling, you really want to be profiling the real release build of your application in as real an environment as you can give it, and as real a load as you can give it. So Visual Studio has really good built-in tools now for profiling. They've been extending that from release to release. If you really want deep, low-level, high-grain control over how you profile and what you collect and what you analyze, Purview is a really amazing tool for doing that. It's extremely difficult to get started with, in my opinion. I've not really stuck with it in any sort of great shape. So my preference, and it's not just because I'm a JetBrains event, is the .trace and .memory tools. These are the ones that I landed on after trying all of these that I found to be the best balance between, they gave me the features I needed. I could figure out how to use them and track my way through the user interface. And ultimately, it led me to the paths on my code that I wanted to optimize. So use whatever you have, use whatever you feel like doing. As I say, Purview is free. Visual Studio stuff is included. The JetBrains products you may already have as well. Other stuff that you might touch on, and we won't really go into this in the session, is ILSpy or Just Decompile or .peek. These are tools that let us look at the intermediate language. So when we compile our C# or F# code, we end up with IL. And the IL is this intermediate stage that later on gets just in time compiled into the machine code as you're running the application on its actual environment. And sometimes by looking at the IL code that's produced by our C# code, for example, we can see issues that maybe things like boxing, maybe virtual method calls, maybe just the number of instructions that we see it generating with our code, and we can tweak our code and see if we can optimize the IL and ultimately hopefully optimize the reduced code at the end of the just-in-time compilation. Not going to need it for all things, just pointing out it's there and it can be a tool in your arsenal. And finally, don't overlook the importance of production metrics and monitoring. These are the thing that you probably want to get in place first, because you want to know, are the changes that you're testing locally and thinking are improving things, are they actually resulting in improvements in production? So what is your memory usage in production? How long does certain key parts of the application take to perform? Have those measurements first, and then you can show that you've actually optimized when you get to production. And most importantly, you can see if you've regressed anything. I work for Elastic. We have an APM product for .NET that you can go and use, plugs into .NET applications and can start profiling them and collecting metrics and monitoring information as they're running. So that's an option. There are many products out there as well. We're also going to be talking about benchmarking quite a bit in this session. And for that, we're going to use benchmark.net. So this is an open source library, primarily for micro benchmarking. And what they mean by micro benchmarking is small units of code. You might be benchmarking at the method level. Sometimes you may be benchmarking at individual lines of code. You generally won't be benchmarking huge blocks of your application that trundle through many methods. You can do, but more often you're tending to look at the really small, fine picture of individual pieces of code. It gives really high performance measurements. It does this by ensuring that it takes measurements after warming up your code, so it's pre-jitted and it's in its kind of final state. It does measurements of its own overhead, so it can remove those. And it does many thousands of iterations of most tests, so that it can benchmark each of your benchmarks in its own process and give you a really good statistical count of how long those methods are executing, down to sub-nanosecond measurements that are really important for individual lines of code. There's lots of ways you can configure it with things called diagnosers. We'll show one of those as we go through the session. And you can use it to compare performance. So if you're deploying your app to different architectures or in different environments where you maybe run different platforms or GC modes even, you can see how your application performs in the benchmarking under those different settings as well. So that's really useful. So you can go get that from benchmark.net.org. And it's used extensively by the .NET team themselves. So the .NET runtime team, the core CLR team, and the ASP.NET core teams all use this in their products to optimize them and give us the performance that we see from release to release. And they leave some of those benchmarks in place and they track them over time. They run them much like you would a unit test to see how performance trends over time. And if they see a regression after a pull request is merged, then they can make sure that doesn't make it to release. So here's a really simple example. We have just a console application that we're looking at here, and we're looking at all of the code for the app. So the way you get started is you pull in benchmark.net from NuGet.org to your console application, and then we set up our main method inside the program class. And all we're doing here is calling the benchmark runner.run method and passing it a type that contains our benchmarks. Now, there are other ways you can have it detect benchmarks in this assembly. For now, we're just going to use the simplest form, but it's very configurable for different needs you may have. And here is our class that contains our benchmarks. I've attributed it here with a memory diagnoser saying to benchmark.net, as well as measuring execution time, I want memory information. I have some setup code. This is all done outside of the benchmark itself. So I'm going to be benchmarking a method call on the name parser. I'm not interested in the overhead of creating the name parser or the string that I'm going to send to it, but I'm interested in the call to one of its methods. And that's what we're doing in this final block of code here. I have a simple method. It has a benchmark attribute so that benchmark.net knows this is a benchmark. And in there, I have the code I want to test. So here I call parser.getLastName and pass in the full name. And this will give me the results that I'm after. So you run benchmark.net, you need to run it in release mode. It will sort of basically stop and fail if you aren't. And then it will eventually give you this output. So it's going to take a while to run each benchmark, because as I say, it's going to do it many thousands of iterations in most cases. It will give you some output. Sort of here it's showing us this was run on .NET Core 3.0. It's an older test that I have. And more importantly, we get our results per benchmark. So here we can see that the execution time of that method was 163 nanoseconds. So we don't know really if that's good or bad, but it's our starting point for an optimization journey. If we feel it's necessary to optimize this, we know our starting point. Because we added the memory diagnoser attribute, we have a few columns now related to memory. These Gen 0, Gen 1, and Gen 2 columns show the estimated number of collections per 1,000 operations in each of the generations of the garbage collection process. So what we can infer from this is everything is falling into Gen 0. It's not living into Gen 1. So the assumption here is that all of our types that we're allocating are short-lived. And we can see, because of this very low number and the fact that this is per 1,000 operations, that it might take around 26,000 calls of this method before we'd introduce enough GC pressure for a collection. It's not a guaranteed number. There's a lot of heuristics that go into GC collections, but it's a good starting point. And then finally, we have the bytes allocated. So this is the thing that most people are looking at, how many bytes were allocated on the heap when this method executed. So one of the tools that we're going to look at about optimizing code today, and the one that we're most kind of keen on, is span of t. So normally when I do this event in person, in front of an actual human audience in a real room, I can ask them to put their hands up if they've heard of span of t. So imagine you're doing that now. I can't see you, but let's imagine. The last time I did this in a real event, I think there were around 1,000 people in the room, and most people put their hands up at that audience. So most people had heard of it. When I asked to keep their hands up if they were using it, pretty much everyone put their hands down. So that was a good sort of sign that many people were not using it. And that's correct. That's the response I'd expect from many of you. Span of t has been publicized really well by Microsoft because it's a key type that they've introduced that's given them the ability to make the .NET runtime and ASP.NET Core so much faster, and to get them at the top of the kind of Tech Empower benchmark results for things like requests per second in Kestrel. So it's an important type from that perspective, but they do tend to prefix all of that information with, you shouldn't need to do this yourselves. This isn't a type you'll probably be using in your code. And that's generally correct as well. I tend to not be quite as cautious as they are. I think it has its place for use in some code bases, not just library authors, but it is an advanced type. It's built into .NET Core 2.1. So any of those versions after that, you've got this type available to you, and you've got a runtime that's optimized for it. But it can be installed with the system.memory package. If you're using .NET Framework, it has a net standard compatible package that you can use as well. The core idea of span of t is that it's going to provide a read-write view over a contiguous block of memory. And the interesting thing about it is it's kind of agnostic to what memory you're looking at. It gives you the same API regardless of whether we're accessing heaps, allocated memory, something that's on the stack, or even unmanaged native memory. So contiguous regions, we're talking about things like arrays, strings, because those are single blocks of memory that we can kind of look at with this view. And you get access to an indexer. You can iterate through the items in this span of t, and you can modify them. It's immutable access to those memory regions. So if you've got an array of integers, you can affect the values of those integers through the span. It has almost no overhead compared to raw array access. There is a marginal thing, but it's very insignificant, and the overall gains of avoiding allocations generally outweigh any risks of the overhead at all. The key operation that you'll hear about when you talk about span of t is slicing, and this is where we adjust our view over that contiguous region of memory. So in this example, I have a new int array of a length of 9. So we create the array, and then to get a span view of that, we call asSpan, and that returns to us a span of int. Span of int is, span itself is a specially designed type, and it will never be allocated on the heap. We'll come back to that. But the important thing is that by calling this method, we're not causing any allocations. We're just getting a span that has a view over existing memory. So the only allocation is the creation of the array in the first place, which generally has been passed to us from somewhere. On that, we can call slice, and slice takes a start and an optional length. In this case, we said we want to slice from position 2 to a length of 5, and that gives us this new view over this internal region of this array. We get back a new span that points to that adjusted region, and we can then work with that span to further manipulate and parse through the data that may be in there. The sort of analogy that I like to use for this is that of photography. So most people have taken a photograph with a camera phone. Some people may have, DSLRs and telephoto lenses. If you're out in the countryside, you want to take a photograph of a really nice landscape, you go ahead, you set up and you take the photo. If something in that frame takes your interest and you want to see it more closely, you have kind of two options. You could walk to the object, which might be, trekking across a number of fields. It might take some time. It might take some energy. It might get your boots muddy. It has an effort involved in it. The other option is that you pinch zoom, or you twist your telephoto lens and you just zoom in and you get the closer view of the object that way. And that is a really quick operation. And slicing is like that because slicing is a constant time, constant cost operation. Regardless of how big the original array is, it's 9 elements here, it could be 9 million. The cost of slicing into it for any length is the same because it's just creating this very simple, lightweight, non-heap allocated type that references a pointer of that in that memory. So it's a very light overhead, regardless of your original array. So let's look at optimizing some code. The demo here is a little contrived. We'll look at more realistic scenarios and code in a moment, but I just want to bed in the idea of this span and also the idea of kind of the optimization cycle. So the requirement we're going to imagine, very real world, I promise, is that we need a method that takes some array from somewhere, and we want to return a quarter of its elements, but starting from the middle. I'm sure you deal with this day in and day out. But it's a good example for the point of understanding the core concept. So given this scenario, a lot of you are probably already coding this in your head and thinking, well, maybe we'd skip to halfway in, and then we'll take a quarter of the elements and we'll return that array, and then we've done the requirement. And this is reasonable. I mean, there's edge cases to this code, but it would work in principle. So imagine we've done this, we've deployed to production, and then a manager comes to us and says, actually, we've realized that this code and this application really needs to be fast. If we make it fast, we get more money. And so we go, great, okay, well, we're now going to go and optimize this code. So here we are, we're back in the first important phase of measure. We know what we're aiming to optimize. So we've already essentially profiled the app, but now we want to benchmark our code to understand if we're going to improve it. So this is a slightly more complex benchmark class than we looked at before. Let's step through the changes. The first thing is we have this size property, which has this params attribute with 3 values. This tells benchmark.net that for every benchmark it runs, we want it to run 3 different times with these 3 different sizes set in this property. And this gives us the possibility of testing outliers and differences between our code base. So while you want to test your common case, let's say that's 1,000 element array is common in our scenario, we want to test the outliers as well, because some changes you make might optimize code at one level, but then you could see a massive degradation on different sizes. So we'll test at 100 and 10,000 either side of our normal average to give us a bit of an impression as to whether our changes work across all scenarios we expect to encounter. We can also set up benchmarks. So this global setup will run once per benchmark. We mark it with the global setup attribute, and all we're doing in here is initializing an array of the appropriate size. This will be our source array that we pass into our method. So that's done. We can now write our benchmark, and this is the simplest form we can do. We're using an expression-bodied method here. We have the benchmark attribute applied. This time we've marked it as baseline. This is our first test, and this is the original code. So we'll say this is our baseline from which we will compare all other results. In this scenario, we've got our skip and our take and our to array, and we return an int array. So pretty straightforward. So we can run our benchmark. So the results here are probably not that surprising. A small array of 100 elements is 154 nanoseconds, 224 bytes. And then this increases as we go to 1,000 and 10,000. And you can see this scales quite considerably each time because we're multiplying by 10 the original input array. So the output array is growing as well. So the thing that we're actually creating as a result of this is getting larger and larger. And that's an obvious side effect of how this code is designed right now. Now, the first thing that we might think of, we might be thinking, we're smart here. We know that skip and take and link expressions have some overhead. So shall we avoid those and see what we can do instead? So we'll create a new array of the appropriate size. Then we'll use array.copy to copy from the old array to the new array in the appropriate places. And then we will just return the new array. And we've avoided link. So we run the benchmarks and we see the results. And we say, oh, OK, our mean has gone down quite considerably. We've win. Allocate on the end there, 128 bytes, nearly half. That's pretty good. Now, the reason we've tested with different params is because we don't want to assume that one result is always going to be totally accurate. Let's see the next one. OK, so we're still quicker, but the bytes allocated is nowhere near as drastically. It's not halved, that's for sure. What we've actually shaved off is about 96 bytes, and what we've really shaved off is the cost of the compilation of the link expressions under the hood. So we have removed some overhead, but not quite as much as we thought. We're still allocating a new array each time we call this method, and that's growing as our input data grows. But the final thing we can do is we can try span-based approach here. So the reason this test isn't entirely fair is that I've decided to return a span event here. So I've made an assumption about this scenario that the caller can actually accept back a span and continue parsing through that span view of the memory to achieve its goal. If they really need a new int array that they're returning, then we're a bit stuck. But in this scenario, we'll assume that returning a span is a valuable return type. And so we can call as span and then slice to get the data that we need. So in this result, the time taken is now under a nanosecond. I think we'll agree that that's a pretty good gain. And we've allocated no bytes at 100 elements. So that's also really good. If we look at 1,000, we're still sub 1 nanosecond. We're still no bytes allocated. 10,000, sub 1 nanosecond, no bytes allocated. Constant time, constant cost operation. Slicing, regardless of that input array size, does not change on how long it's going to take. On my machine, when I measured it, it's around the 0.9 nanoseconds. And we haven't allocated anything because all we've done is narrowed our view over existing memory and return that view back to the caller. So again, it only works if the caller in this example can do something with it. But in more real-world applications, the application of this across your code can be quite significant. Now, we can also use spans over strings. So we can call as span on a string literal, on a reference to a string. And what we get back is a read-only span of char. So char, because a string is ultimately just a sequence of char characters, and a read-only span because strings are immutable. And so the compiler enforces this rule that we can't return a read-write span view over that memory region, because that memory region is still accessed by the string, and we'd be mutating a string under the hood. And that would really mess with a lot of your other code. So to maintain the fact that strings should be an immutable type in .NET, you can only get a read-only view over them. But this is still valuable for parsing through those strings. So in this case, imagine we wanted to get the sort of last name out of this string. So again, a trivial way of doing this would be to look for the last index of a space, assume that everything thereafter is the surname, and then we just slice from that position. And then we have the data that we need. So then we could do some further parsing on the string. There are some limitations to span, and these are just important to be aware of because these will come into effect. So it's a stack-only value type. It uses this keyword ref struct, which means it's a struct that starts off and only ever lives on the stack. It can't ever end up on the heap for any reason. And so that requires that we have C# 7.2, which gives us the ref struct keyword. And it also means that anything that is a span or uses a span can't be boxed. It can't be a field in a class or a non-ref struct because those fields are part of the class on the heap or could end up on the heap if the struct gets boxed. It can't be used as an argument or a variable inside async methods. This is probably the big one a lot of people run into. We'll see how to combat that in a moment. The reason for this is that the state machine behind the scenes that gets built when your code compiles is going to be a struct or it's going to be a class, depending on where you're running this code, and those could end up boxed onto the heap. So it would break the rules above. And similarly, if we capture it inside Lambda expressions, that creates a closure class that we don't want to have as well because we break the rules again. So the way around this is we can use this type called memory of T. Fundamentally, it's very similar to span, but it can live on the heap. It's a read-only struct, not a ref struct. The reason you wouldn't do this just as default is it is slightly slower when you're slicing it. It's not as optimized as span. You can call span on it or get the span property, though, to see a span over the same data, and we'll work out why that's useful in a moment in this example, actually. So here we have an async method, and we'd love to pass in a spanner byte that we do something with. The compiler is not letting this happen. We're breaking the rule of having a parameter here that's a span inside an async method. So we're going to swap to memory of byte instead. And we can now slice and work with that data if we want to. If we really want to optimize, then in realistic terms, in most async methods, they're async for a short period of time when you're maybe going over the network or to a file or waiting for some I/O to happen. But then the actual processing of the data that you're getting, you can kind of do synchronously. And so what you would typically do is create a non-async method that does accept your span, and then you would pass that in from your async method. Now, you can't do this, which is declare it as a local and then pass it in. But what you can do is just pass this in this way, and the compiler knows how to handle this. Or similarly, we just pass in the raw data .span and then work with it inside the main method. So this is how you get around that sort of async limitation. So let's put all of this into practice, and I'm going to kind of jump into some code now reasonably quickly. You can go and check out this code yourself if you want to, but the scenario, actually, let's show you the scenario before I show you the code. The scenario here is that we're going to read messages from a queue, SQS on AWS in this case. We're going to deserialize the JSON message, and then we need to store that message somewhere into an S3 blob store. To name that, we need an object key, and we're going to derive the key from properties of the message. So here's the original code. I'm just going to step through it very briefly. We have this source event context. This is just the property that contains the data that we have here that represents what we're getting in the message after we've deserialized it. We're going to say that we're going to use 4 or 5 elements for the key. It's optional. If the event date is there, we're going to use it. Otherwise, we'll just use the other properties we know are definitely present. And we're going to create a string array of the appropriate number of elements. We're going to call this getPart method, passing in each string for the parts that we want to use in our key. And getPart down here is this fairly straightforward method that says, if it's null or empty, we're going to use a constant unknown value. But if it has a value, remove its spaces using string.replace here to remove spaces with placing with underscores. And then we're going to check it's valid with this is part valid method, which is just using a simple regex pattern. And then we're going to return the value. These get stored into each element of the string array, including the date if it's present by calling its toString method. And then ultimately, we are going to use string.join to join those pieces together. And we want them lowercase, so we call toLower to finish off. So this is the original starting point. Here's the new code, and we'll again briefly step through this. You can go and pull this down and have a play around with it. There's some optimizations here I'm not going to even worry about. It's a weird compiler optimization that avoids a mem copy. The key stuff we're going to look at is this is a little longer than the last code, probably 2 or 3 times the length. So more complex code. Fundamentally, it's quite similar to what we have before, though. But first, we're going to calculate the string length that we need. Once we've got that length, we're going to allocate some memory where we're going to use as our working buffer. So to be really optimal, we're going to say if we're under this value here, 256 characters, we're going to stack allocate a character array for this. So we're not going to heap allocate any arrays. And we can use stack alloc without the unsafe keyword here because we're returning it as a span of char. And this is, the compiler knows that this is kind of memory safe. Because the span can't outlive the stack allocated memory it's going to reference, because it is itself only going to ever live on the stack. It can provide these type safety and memory safety guarantees. The fallback, which is unlikely, is if we can't allocate on stack because it's too large, we'll create a character array. The reason for this code is really be careful with stack alloc. Just because we can doesn't mean we should. Allocating large amounts of memory there could cause a Stack Overflow exception in your code, and then you'll end up on stackoverflow.com trying to work out why. There is a finite amount of memory there, so make sure you use these bounds checks before you use it. Then we're going to build our string parts. So the way we do this is we pass in the source string that we're using, we pass in our span, which is our working buffer, and our current position by reference. And that ends up in this method down here, which ultimately what we're going to do is similar to before, but now in an optimized way. We're going to first check if it's essentially 0 length or all white space or empty. Then we use unknown. Otherwise, we're going to check if it's valid, but not by regex this time. This time we'll just use, iterate through the characters and see, are they a letter, a digit, or a space? If so, we're good. Otherwise, we're invalid. And in the case where we're valid, we're going to use this new memory extensions.toLower invariant to copy the input value into our output span. by slicing it at a current position. So we're going to keep slicing our way through the span as we write into it, so that we're always incrementing and appending to the end. And that's fundamentally it, really. For the remove spaces, we're now using the index of to see if there is a space. And only if there is, we're going to keep looping through until we've got rid of all the spaces. And at each character in the indexer, we just replace that with an underscore if we find a space. And we can do this because we're not working with a string yet. We're working with a char array on the stack that we can later convert to a string. And we do that at the top of the code here. So after we've done our building of our method, we add the date using this try format here, which again is an optimized version that takes a span as the place to write the formatted data. And ultimately, then we call this toString method. So we do allocate here, where we call toString, but the rest of the code is optimized. So the thing you're probably really keen on is how much of a gain did we make? And here we are. So the original code took around 1,000 nanoseconds to run. The span-based approach is over 2 times quicker, pretty good. The allocations are also a little bit more significant, actually, almost or around 6 times less allocations, 192 bytes on over a kilobyte in the original code. Now, you might say that this isn't worthwhile. Less than a kilobyte of savings for this string allocation is probably not worth it, but this is processing from a queue. And this particular service does 18 million messages a day. So if we calculate that saving up, that's over 17 gig of daily allocations that we reduce just on that code path, just with those optimization techniques. So at scale, these things can have a gain. And this led to the fact that we can potentially run this service on smaller container instances in our cloud. The next thing I want to talk about is ArrayPool. We'll do this reasonably quickly. It's pretty self-explanatory. In situations where you need an array repeatedly, you should always try and reuse the array. So if you're doing stuff in a loop and you can reuse the same array, great. But sometimes we're doing stuff that's going to be sort of concurrently accessed. So maybe in an ASP.NET Core application, we have an action method that gets called by all sorts of threads as different requests come in. In that scenario, we can't reuse the same instance because that's not going to be thread safe. But what we can do is use a pool of arrays to give us a fresh array each time we need it that we then return back, so that we're not allocating new arrays each time. We're just reusing arrays as we can from the pool. It's found in the System.Buffers namespace. It's really easy to use. You get an array pool of T, whatever sort of type you need. You access the shared array pool generally, and you rent from it with a given length. In this case, you are likely to get back an array that's bigger than the length. And the reason for this is that ArrayPool needs to buffer in different buckets those arrays. So it couldn't give you any size you ask for each time you ask for it, because you're unlikely to need the exact same size each time. So it's going to say, well, I'm going to put an array of 16 and then a bucket of 32 and 64, all the way up to about 1 million, doubling each time. And it will give you the closest, smallest array that is in the pool that's available. So you will likely get an array that's bigger than what you need, and you need to track your position within that as you're working with it. When you are done with it, you return to the shared pool, optionally clearing the array. So by default, the arrays are not cleared. Be aware of that. When you rent from the pool, you may have data in the array. So again, it's important to know how much you've written into your array if you're using it as a buffer, so that you only ever access that portion of the array when you then do some further work with it. To use it, fairly straightforward. So this method gets called really, really often, and it needs a temporary buffer, maybe to do something like read from a stream, perhaps in a real application. So in this situation, it's allocated a byte array of 1,000. But what we could do instead is rent. So by going to the array pool of byte.shared, we get the array pool. We rent from that an array that's at least 1,000 bytes long, and then we do something with it. To ensure that we are returning it, we make sure that regardless of whether we have an exception or not, we return this thing to the pool. So typically we use this with a try finally. Inside the finally, we do our return to the array pool of our temporary buffer. Next up, System.io pipelines, another one that I'm going to plow through so that we can see the actual code. So the reason this was originally created was the ASP.NET team were working to improve the request per second in Kestrel. Kestrel is the ASP.NET Core web server. It's doing a lot of network I/O. That's all its job is, to listen to requests as they come in and pass them through into ASP.NET Core. The team, particularly David Fowler, realized that they could optimize Kestrel and avoid using streams for all of the transport layers, passing off through this thing called a pipeline instead, which basically optimizes the code. And for their scenario, they saw around a 2x improvement. You could achieve this with streams, but it's a lot of work to do it. Pipelines makes it a lot easier. And basically, it just removes boilerplate code. And the main difference is that unlike streams, what pipelines does is it manages the buffers for you from the array pool. So we're already getting the advantage of the fact that where with streams, we would create a new array and pass it in as the buffer for the stream to use when we're reading or writing. With the pipelines feature, we don't do that. It gives us blocks of memory that we work with. And there's two ends, a writer and a reader. Write, we have the pipe writer we call get memory, which returns us a memory of byte. Memory here because this is almost always going to be inside some kind of asynchronous method because we'll be reading off of a network file, a network socket or a file. So we get memory byte because that's safe. We write into that however we want to. We could convert it to a span in a non-async method as well. But when we're done, we just advance by however much we've written and then flush it. And this says to the pipe, okay, I've written 1,000 bytes and they're ready for the reading end. The reader sits there with this read async call. So it's a non-blocking asynchronous wait until there's some data in the pipe. Once there is, the callback gets activated and we get back our read result. From the read result, we access the buffer, and the buffer is this read-only sequence. Why a read-only sequence, not the memory that we put in? The reason is because the pipe in advance doesn't know how much data you're going to give it. Some requests may be huge, some files that you read might be larger than others. So the pipe doesn't know in advance what buffer size to use. It just allocates a buffer, and once that's full, it will allocate another buffer. And it keeps track of all these in essentially a linked list. So we have these buffers spread across memory in their own little contiguous blocks, but not one contiguous block. But this gets represented to us as this read-only sequence, which is this linked list of these memory regions. So now we can access our way through the sequence that way. I can show this in action. So we have another scenario that I used to work on where we read an S3 file, which was tab separated format. We decompressed the file and read 3 columns from each row and then indexed that data into Elasticsearch. And we wanted to optimize the reading of the file. So if I jump back to the code example here, the original code is actually really short. It fits pretty much on a whole, well, 2 screens because I'm on a massive font size. We read the file, we decompress it, we access the memory stream, and then this original code was calling toArray to get all of the bytes in the decompressed stream. In order to pass that in to get a string on UTF-8, so to get the encoded string. Now we have a full string. It was passed into this this library here. So this code is using a library called Tiny CSV Parser, which at least at the time needed strings, I think, to work. So once we have that string, it ends up in this parsing logic. And the key bit of this is that in parse, that library gives us this really nice way to say, okay, split each row on the new line character. That's a line of data. And then when you're mapping from each row, find the values at each tab. So the tab 0 is the date, and then tab 1 and tab 10 are the 2 other fields that we care about. Everything else we don't care about. So that's the original code. It's pretty self-explanatory, and you could read through and understand what it's doing. The new code is a lot longer, but it's fundamentally the same idea. So we get the decompressed stream. At this point, I use this connector to access that stream using a pipe. So at this point, usually streams are still going to exist in somewhere in your code, but you can convert them to a pipe reader at an appropriate point. So here we pipe reader create, and that gives us the reader. We then read async, so a non-blocking call here until there's data on the pipe. Then we get the result buffer, and we call our parse lines method here, which, highlighting the wrong thing, comes down here. And all this is saying is essentially, give me a sequence reader, so something that knows how to make parsing through those sequences easier. Try read to any on that sequence reader, takes the thing that we're reading to, which in this case is the byte that represents new line. So keep reading until you find a new line. If you don't have it, exit the loop and wait until more data becomes available. So we just avoid telling the pipe that we've read anything in that situation. We've read it, but we've not consumed it. We want it again, so that later we hopefully have a complete line. And when we've got a line, we parse into parse line here, which is ultimately now using a span to look over that byte data as we have it. And we're just counting manually when we see tabs. So we're looking for the index of the tab character, or the first index. And we know that the first tab represents data that we're going to want. So we now do need a string at this stage because we're going to create an object that has the strings that we're going to send to Elasticsearch. But using this range here, we can say, give me everything until the first tab character, because that's the data we want. And then it's going to move on. So down here, we're just going to slice the line and say, right, move to the next section. And then we locate the next tab, and then we grab from there. And similarly to tab 10. After tab 10, we don't read the rest of the line. We know we've got the data we want. I know I've scanned over it quickly. We can go kind of, as I say, you can go and look at this code yourself as well to try and get a feel for what it's doing. But the concept is pipe readers and span usage there. So let's see the advantage this gained. So the original code was out 8.5 seconds. Not bad for, we're actually testing 75 files with 10,000 rows here. 8.5 seconds is not too bad. We got it down to under a second. Great, go us. The key thing, if you look at these allocations, in that original code path, every file we read was read into a stream. It was then converted to a full byte array, just in order to convert it to a full string that represented the whole file. Then it was parsed. And there was obviously here 7.2 gig of allocations because of that. The new code, 242 meg. It still sounds high, but that's 30 times less than what we had before. And 203 of that are the string allocation costs of the actual strings that we do want, that we need to create the objects that we index to Elasticsearch. So this is a good gain in our scenario and something that's potentially worth doing. Some of the last stuff I want to look at then is looking at System.Text.Json. So these are new APIs that were introduced in .NET Core 3.0. You might question why Microsoft have introduced their own APIs. There was a long discussion about it. Ultimately, James, who originally wrote Newtonsoft.Json, wrote a blog post. He now works for Microsoft, to be fair. But he wrote a blog post explaining that this is a good thing. We need a JSON library ideally in the box so people can just use .NET and access JSON. And secondly, there's a lot of optimizations that can be now made if you redesign how JSON deserialization works, taking into account all of these new types and optimizations that we have. Going back and retrospectively doing that to Newtonsoft.Json without breaking the world would be quite painful. So this is in the box with .NET Core 3.0 and greater. There's a low-level set of APIs that we'll look at in a moment called UTF-8 JSON Reader and Writer. This is for raw writing of data at the very low level, which means you can avoid most allocations. And we'll see how that works in a second. For reading data, we can also use this middle level JSON document, which is a sort of document object model representation of the JSON that we have that we can then work with. This, for certain sizes of JSON data, under about 1 megabyte, I think, is essentially 0 allocations in the way it works. And then the normal high-level types, JSON serializer and deserializer, are typically what you'd work with. They sometimes still more performant than Newtonsoft.Json was, but they're not as good as the low-level stuff. And you can pitch your code as to where it's appropriate for what you're building. So the last scenario I'm going to show you is, imagine a situation, well, we had a situation in my old job where we were indexing data to Elasticsearch. We were using the bulk index APIs to do this, which means we can send about 100 documents a time, I think, or maybe 1,000 we were doing. But you can send a single HTTP request to index lots of documents. And what you get back as your response from that index request is JSON that tells you how long it took, were there any errors for any of the documents, were just a kind of yes, no, and then an array of all of the sort of metadata about each item that was sent in. And that basically gives you the error information if it's present. Now, when we were processing this, we realized that actually in the 99% of cases, the request was succeeding, but we were fully deserializing the whole response in order to figure out if it succeeded, because we just wanted to know, true or false, was it a success? So we looked at optimizing this code. So I've got the original kind of code here. Again, it's a simplified form. This does actually fit on one screen, even at this huge font size. Basically reading from a stream, we're going to use, in this case, it's Newtonsoft.Json, so we call it deserialized method. We want an instance of bulk response from the data from the reader. And once we have this response, we can access this. This is the object representation of it. And you can see that we're going to have these two properties, how long it took and were there errors. And only if there are errors, or if this is true, would you need to inspect this collection. And as I say, we probably don't need to do that a great deal of the time. So in the happy path, the 99% case, we can just say, well, if there's no errors, that property is false. We're going to return true success and return back an empty string of IDs. There's no errors found. Otherwise, we figure out which IDs were actually the failures by inspecting all of those elements, and then we can return the errors. The new code is over here, is considerably longer. I'm just going to scroll for effect. I know that won't show up very well on YouTube. It's a lot longer. It's a lot more verbose. It's harder to maintain. So again, use with care. This one uses an array pool. So I rent an array. In this case, I know the maximum size because this is demo code, but I'm renting an array of the appropriate length of bytes. We're reading, in this case, from a stream. We could use pipelines here like we saw in the last demo. But in this scenario, I'm using my ArrayPool buffer so that I'm not allocating the buffer each time. I'm using the pooled version. And once I've got that, I'm going to read some data. I then call into parse errors. And what this code is going to do, you can see it has this horrible signature where we take a read-only span of byte, the data that we've read from the stream, and all of these ref balls and things. These are basically my state that I could wrap up into a more formal object probably. Ultimately, though, what we're going to do is we're going to access the low-level UTF-8 JSON reader, which is re-entrant. So you can say, have I got the complete JSON data? So have we read the entire stream? If we haven't, we can actually just keep calling this method time and time again. And my own method here is also re-entrant by passing these state variables in. We can keep reading until we've consumed the stream, but we don't have to wait for the full stream to start processing. So that's one advantage. So we have the reader. We're calling read on there, and when it returns, when this eventually returns false, it means we've read to the end, which means we're on the final block, we've seen the final object bracket, so we've read to the end. So if we've read to the end and we've detected the errors property in here, or until we detect the errors property in here because it's a while loop, we're going to keep looping through. And what we're going to access is the JSON token. So each read pulls back the next token. And you can see at this level, we're having to inspect, are we at the start of an object? Are we at the start of an array? Have we found a property? And this is the interesting one. So if we find a property, if the value of that property is sequence equal, so we're going to do a span-based check here, to the errors property name, so the bytes that represent the word error or errors, then we know we found the errors property. This means, because I'm tracking my state, that the next time I come through this read loop, the next thing I'm going to read is going to be a Boolean value, either true or false. Have we got errors? And if it's false, then we know that has errors is false. Otherwise, we know has errors is true. So we're reading the data until we get to this property, and then we're going to break out of the loop, which returns us back up here. And then after we've done our parse, we now have this found errors property. So we know, have we found the errors property? Did it have errors? If no, we don't read any more JSON. So what we're actually looking for is in the first 20 bytes of JSON code is the actual answer. In the 99% case, that's going to be false, and we don't need to read the rest of the JSON array at all, the JSON data at all. In the unhappy path, yes, we still have to keep looping, and eventually we're going to find each item and find the ID out of it. And you can see how that code works if you want to. Again, it's not production code either, so use with some care. So what are the results of doing this? Well, let's assume the failure scenario first. So in the case where there were errors and we had to read through all of the JSON, then the original code was 428,000 nanoseconds. It's down to a third of that in time. Again, not huge numbers, depending on how often this is called, maybe useful, maybe not. But we have quite drastically reduced our allocations here. So 114K down to 16K. A good start. I mean, I know certainly that could be further optimized in the code that I've written, but it was a good sort of proof of concept. The scenario we're interested in, though, is the 99% case that we've indexed the documents and they all succeeded, which is generally true for our situation. And so in this scenario, where we do get a has errors false in that first few bytes of the file, you can see now we're down to only 485 nanoseconds. Because we read from the stream, we read those first 20 bytes, we parse them through our UTF-8 JSON reader, we find that it's false, and we just stop. There's no more work to do. When we've short-circuited a big chunk of code. In the previous example with JSON.NET, we've deserialized the whole JSON response, regardless, just to find out if that property is false, essentially. And I know there's ways we could have optimized that with Newtonsoft JSON as well, but in this case, System.Text.Json gave me even further gains. Allocations practically zero. I think I figured out where that 80 bytes comes from actually when I was going through the code earlier. I do allocate a list at one point. I should reuse probably an empty list and an immutable list. for the happy path, and then we'd probably get that down to 0. So a pretty damn good gain, I think. So I appreciate I've shown you a lot, and I've shown you a lot quite quickly. I do have a habit of trying to pack information into sessions, so do rewatch it if you miss some stuff. Do download the code and take a look at it and understand what it's doing. But one of the important things that I want to leave you with is, great, I now know I can do this. How do we actually start doing this in our business? How do we get people to allow us to do this cool stuff? The first thing is, obviously, think about whether you should be doing cool stuff. You might not need to for most of your applications. But if you have a scenario where you do know that there's a cost in terms of compute power for scaling something, or something is taking a long time and it has a potential cost impact to your business, if you could improve your business by getting results faster to whoever needs them, think about those types of scenario and think about the code that's behind those processes. Go in, identify a quick win in one of those. So grab the code, profile it, find out where the hot path is, find out where the most time is spent and the most allocations occur, depending on what you're trying to improve. Use a scientific approach for that. So use a good profiling tool like .trace, .memory. Use benchmark.net to measure the piece of code that you've then identified on the hot path that you have a suspicion could be improved. Get your benchmark, optimize it, and then once you've established what gains are possible, go to the business by putting those gains into monetary value. I think we all know that if we went to certainly a senior management position, a non-technical manager, and said, I can save 200,000 nanoseconds on this code path, and it's probably going to save 1,000 bytes of allocations, they're probably not really going to care or understand what you're trying to tell them. So figure out what the monetary value is and establish a cost to benefit ratio. So do this as a prototype. Do this as time box an hour, a few hours to try these attempts. Once you've done that, your cost to benefit ratio could look something like this. So the process I used to work on was this one microservice. It was handling 18 million messages a day. The techniques I've shown you today, all of them are part of a set of prototypes I made based on some of the work that needed to do. Not all exactly the same, but the ideas are there. And then what I did was figure out, okay, based on these examples, my best guess is that I can probably get to about 50% of overall allocations. And I can pretty much assume I'm going to double my throughput based on my early execution time improvements and then throughput measurements as I'm doing the work. So I had a sort of a rough idea of my potential gains. And then instead of going to them with that, I sort of said to the business, well, I've done some stuff. I think if we applied it, this microservice will actually need to be scaled less at high throughput loads. And that's one less VM that we need to scale onto. So by avoiding that one less VM across the year, the size we were using around $1,700. Now you might question, is all of this effort that I've just shown you worth $1,700? Probably not. Your developer time may be higher than the value you're saving, but obviously year on year, this game will get you there. And if you're building something like microservices, as I was, a lot of the techniques I saw could be applied not on just one microservice, but maybe tens or hundreds. And so $1,700 can start pushing into maybe 17,000, maybe more. Those are numbers that the business might be more interested in. And you can apply the same sort of techniques across, for example, queue reading, very common problem, parsing the JSON from it, very common problem. Maybe some of your techniques would be good if they were applied there. Ultimately, what I'm saying is that scale matters here. So a single microservice could save you a little bit, but can that be scaled across your code base? Or is it a critical service that, shaving the execution time or increasing the throughput gives you a benefit? So lots and lots of stuff to digest. We will have a time, hopefully, for a few questions. But in summary, if you're doing performance optimizations, you should always be measuring and not making assumptions. Assumptions are really dangerous. Don't do it. Everything you should do should be backed up by profiling and benchmarking before, during, and after your changes. Be scientific about how you make those measurements. Benchmark.net is the perfect tool for scientific, accurate, repeatable results. And you can even keep those benchmarks as part of your CI process that run on each check-in to see if your code continues to maintain the performance you expect. If you're optimizing, focus on the hot paths. It's really easy to get sidetracked by something that looks like it's a big problem, maybe allocating a huge byte array. But if it's only done once at startup, optimizing it's not really worthwhile necessarily. When you can, and in your situation you're optimizing, one of the quick gains is not copying memory. So not copying between arrays, not keep copying off streams into different buffers. Spanity is a really good way to avoid that, and just change the view over existing memory, parse your way through it till you find what you need, and then you can work with that reduced data set without having copied everything. Where you need to, and you're using arrays, array pools are a good example of way we can easily reduce allocations with very small code changes. Pipelines, great tool for IO scenarios. If you're doing that kind of work regularly, go and look at it. It's probably more niche, I would say, than most of the things I've shown you today. And System.Text.Json, they do perform better in a lot of the tests I did. Measure it if you want to try it, apply them, but prove it with numbers as well. One thing I do recommend is this book, Pro.NET Memory Management by Conrad Kokosa. It's a good book. I've got it here because I just want to illustrate the sheer size, weight, beefiness. It's over 1,000 pages of high performance goodness. It explains how memory works in computer terms, in .NET terms, and then how to optimize for it. It's a great book to carry around. It's good exercise. It acts as a weapon if you're attacked at night, and it's full of good information. So I really do promote it. It's where a lot of my initial research that I've used in these prototypes came from. Ultimately, I'm going to kind of say thank you. We'll hand over to questions. Just a reminder, the bit.ly link there, hyperf.net, will get you all of the stuff I've shown you. So if you've missed things, you can go back and get them, and feel free to reach out if you're watching the recording at DJ Gordon on Twitter. So with that, I guess we can probably go to questions.
Great. Yeah, we can. Thanks, Steve. That was great.
You're welcome.
Both interesting.
That was a fantastic session.
Partially mind-blowing too.
I want everyone to leave the day partially mind-blown.
And it's always good to give some self-defense tips as well. So thanks for that one. Right, we have some questions.
Yeah,
we have some questions we can just jump straight into. First one, the object key generator example you were showing there, and in fact, some of the examples you're showing there, they're quite extreme. There's quite a few changes going on compared to the original version. You also mentioned with the object key example that it could save gigabytes of data. So was that one actually a production example?
That did end up in production. Yeah, so the prototyping was the early phase, which is kind of what of the code I've shown in here, because it's a little bit more constrained. And then we kind of shored that up. So another key tip that I probably didn't mention is have unit tests around the code you're about to optimize. Make sure that after optimizing it, the code still does what you think it should do. It's very easy when you start getting into like spans and looking at sort of byte arrays of data that you miss something and you garble the whole output. So yeah, unit tests first is really important.
There were a couple of comments in the stream as well that maybe the regular expressions might help you as well there. So if you're dealing with regular expressions, unit tests are also going to be helpful with that too, I think.
Sure. Yeah. Yeah. It was a slightly slimmed down, contrived example of the whole thing, but yeah, definitely something that we put into practice, and we did actually reduce the scaling and the memory usage of our container instances that one went into.
Yeah, I got to say as well that that's actually. I think that's a great way of getting across this sort of performance thing here. Is coming from like a techie background, like we probably do, the people watching this stream. It's very easy to want to improve performance just from a technical point of view. Better performance is obviously better. Or if you've got an interactive UI, like obviously we do with some of the IDEs, then again, performance is obviously better. If you've got a server scenario, sometimes you don't always see that. And so looking at it from a cost point of view as well is a great idea. It's a great idea for getting the buy-in to be able to, to have the permission to do the refactorings in the first place. Yeah. But also to show that there's a real benefit to doing this, not just because we think it's cool.
Yeah. And the approach I took with this was very much, lunchtime hacking to say, okay, I've learned about this span. What do I think I could apply it to? Okay, here's an example, and sort of try a few things out. A lot of that's good fun, and I encourage people to do it. And as I stress, doesn't necessarily mean that everyone should be throwing this type of code out to production tomorrow, or anyone in the near future. Use it all with care. But there are certainly good situations that we found to apply it in certain microservices in particular.
I have a great performance tip return null or just return? Yeah, I'm just kidding. I also have one more question, actually two, but in between, Matt. We have one question, which was, you mentioned not to use span of t in your own code base. Would you recommend using it if you're building libraries and frameworks for others, or is it best to not expose them?
So certainly Microsoft do advocate its use across library use cases. You want your libraries to be good, they're likely to be installed by lots of people, and more performance for free is a good thing. It's certainly one of the things I'm focused on now at Elastic in the .NET client as we move that forward. What can we do, much like the runtime team have done at Microsoft, much like ASP.NET Core have done? We just want people to upgrade to the next version, and suddenly we're allocating less. And that's kind of, I think, a good practice for most code authors of libraries. Do you have to expose those APIs publicly? Sometimes yes, sometimes no. So a lot of this stuff you can keep internal and you can make the gains in your own code where it's controlled, but some libraries like JSON parsers, maybe you write a YAML parser or something, you might want people to be able to pass you a span of bytes or a span of characters as an input to your methods that you then process. And that avoids them having to allocate potentially an array just to pass it to you as an argument to your method. So what the runtime team have done, and what I certainly would look to do as a sort of library author these days, is add overloads that accept these things. So where you take a byte array now, it's good to accept a span of bytes, and then you have some common internal code that then uses whichever it's given, which is generally going to be very similar code, because you can call as span on the byte array that they parse you as well. And then you've basically got comparable code internally.
Yep.
Cool stuff. Sort of, I guess a follow-up question with some of the production code you're talking about there. Are you happy with what you've got at the end? I mean, obviously, saving some money is going to be a good thing, but that's not all you've left with. You're left with a different set of code base you've got now, and so on. So are you happy with? And you talked at the beginning about trade-offs between performance and readability. So are you happy with where you've ended up with this?
Some of it, yes. Some of it, no. I've moved on from the company now, so I don't know what fallout occurred after I left. But
ship it.
I do know, I did speak to one of the developers that I used to work with, and they did have to tackle a small change to one of the services I'd gone in and optimized. And they were not as happy as maybe I would like them to have been about this code that they had to try and work out. So it's definitely true that, by doing this, you are making a decision that should be assessed at a relatively senior level within your team. Is this something we want to do? Is this a trade-off and a burden that we accept as a result of taking this high performance code on? So certainly, I think probably I got a little overzealous with all the stuff that I was able to do, but certain services, I know they're still operating that way today. The benefits were worthwhile. Some of it they may well have adjusted so that it's more maintainable. So definitely assess up front where you can apply it. You need to do that sort of analysis of what can we save and how often are we likely to have to manually figure out what this code is doing again, because it's very hard to maintain those much longer methods, those much more condensed pieces of code. It's much harder to kind of parse that in your brain when you're trying to pick it up again.
Yeah, there's a lot to be said for familiarity of knowing what you've already got with your existing code base, and then changing it up for these kinds of things. And yes, it's very easy to get a bit overzealous when you first start with these things. I remember making a bit of a mess with some RX back in the day, which I had to go back and fix at a later date. Before I left, they made me fix it because nobody else wanted it. Yeah, but yes.
I have one more question, which is, do you have any practical tips for performance measurement on networked services?
Not a huge amount. It's something I'm starting to think about at the moment, funnily enough, as we're writing a library that's doing pure HTTP. For the most part, most of that work is still going to sit on top of Microsoft libraries. So let them do the hard work, run on top. If there's a good library in the framework for doing HTTP or doing what you need to do, most of the time it's best to stick with that. If you're really down at the raw level, I've been using Wireshark recently to capture TCP and HTTP packets and understand a little bit more about some of the actual networking overhead of some of the stuff. There's some good stuff as well. I think Tess was showing it off. The .NET counters feature is a great way now with .NET 5. You get counters around how many DNS calls are being made, how many HTTP sockets are being used. So you can go and attach to a running .NET process with the counters and get an impression of networking use at that level. And then something like Wireshark's quite good for really low-level packet analysis after that. But as I say, try and stick to the built-in stuff. I know Microsoft are doing work around a low-level HTTP client that I'm watching extremely closely. Those sort of gains are the sorts of things I would look to do, rather than rewriting my own HTTP library, for example.
I understand. Would something like telemetry also fit into that category of?
Yeah, I would say for all of this stuff, having telemetry in production for as much of it as possible is key. So, if you can track how many network sockets are open from your app when it's running in production, how much memory you're using on the heap, how many garbage collections are occurring. Certainly, those were metrics I tended to put into these high performance services, so that we could track those over time. We could look for regressions. We were pushing almost daily to some of these during early development. We could see if we were improving or, as I say, degrading performance on those. So yeah, always have those. I think it's very easy as well. Some of these techniques, you might improve the stuff on your local machine. It works on my machine, great, ship it. Having the telemetry in production is also key to know that, yes, what was running great on, say, a Windows box, now when it's deployed as a Linux container in a constrained environment, still has the same advantages that you first saw.
Yeah.
Okay, I think another quick question. Is there a repository or blog where I can see before and after comparison with optimizations as you've just shown? So I know that your bit.ly link there, the highperf.net, Martin's just posted that into the comments. So if you want to find that, you can. I'm not quite sure what was on that link there. Do you have any kind of examples in that, or is that the slides?
So most of the slides kind of lead you up to the code samples. The actual code repository is there that shows you those before and after classes of the things the benchmark should run on your machine, and you can kind of tinker with it. As I say, it's demoware. And a lot of the stuff that I've shown is on my blog as well. So if you kind of search performance as a tag on the blog, you should find posts about most of what I've shown there, the usage of span, usage of ArrayPool, that kind of thing.
Great. Speaking of benchmarks as well, you mentioned running your benchmarks as part of CI. Does benchmark.net have the ability to kind of to break your CI if things are if the performance is degrading there at all?
Yeah,
is that built in, or do you have to add that yourself?
It's not necessarily built in. I know colleagues of mine actually at Elastic had been working on a package that could take the output from benchmark.net as part of the CI process. It's basically a set of XML files and things that you could interpret. I haven't tackled it yet, but it could certainly do so. I mean, my theory is maybe we could run them as GitHub actions. The challenge with CI for the benchmarking is you want your benchmarks to run on a consistent environment, and you don't want other things running on the machine you're benchmarking on. And so ideally you want to spin up an identical VM or something each time. And even then, you could have differences between runs, different, subversions of the VM that you're getting given by your hosts. And so that's the challenge I've yet to work out. So Microsoft, I know, do this, but they have a whole benchmarking environment that's sitting there running warm all the time, and they can run continuous integration on that, knowing that environment is not, changing from run to run, and then they can get the consistent results. So my theory is GitHub Actions isn't going to solve it for me, and we might have to think about a dedicated VM under the hood for that. But it can be done. I just haven't done it yet. But you can check what Microsoft are doing in some of their repos and see if there's any examples in their kind of build area.
Sounds good. Thank you.
All right, cool. I think we're out of questions. We actually have a couple more on our list, but we should bring in our next guest. Steve, thank you from every one of us from our team.
Thank you very much
for being here, and it was really interesting listening to you. And see you around, right?
Thank you. Thanks for having me.
Thank you.